Right now, the Earth is moving through space at roughly 107,000 kilometers per hour, and yet we are sitting inside one of the most densely populated regions of the observable universe. Billions of stars, hundreds of billions of galaxies, vast clouds of gas and dust, and invisible rivers of dark matter all surround us in a cosmic web of matter that looks, from a distance, like the inside of a sponge. But here is the part that rarely gets mentioned. The space between those sponge walls is not just empty. It is dominated by enormous voids, gigantic volumes of near-total nothingness that make up the overwhelming majority of the observable universe by volume. Most of what exists is nothing, and that nothing is not passive. It is active, growing, merging, and shaping everything we see. To understand cosmic voids, you first need to understand the large-scale structure of the universe. When astronomers began mapping the positions of galaxies in the 1970s and 1980s, they expected to find something roughly uniform. The idea was that galaxies, while clustered here and there, would be spread more or less evenly across space when you zoomed out far enough. That assumption turned out to be wrong in a dramatic way. What astronomers found instead was a web, a vast three-dimensional network of filaments, sheets, and nodes where galaxies and galaxy clusters are strung together like beads on threads. And those threads intersect at massive knots called superclusters. Between these structures, taking up the space between every filament and sheet, are voids, not small gaps, not minor absences, enormous bubbles of space that contain almost nothing at all. This structure is called the cosmic web, and it is one of the most striking features of the observable universe. Understanding how it formed and why voids exist within it requires going all the way back to the beginning. Approximately 13.8 billion years ago, the universe emerged from an extraordinarily hot, dense state and began expanding. In those first moments, the universe was nearly, but not perfectly, uniform. There were tiny fluctuations in density, regions where matter was ever so slightly more concentrated than surrounding areas. These fluctuations were quantum in origin, meaning they arose from the fundamental uncertainty baked into the structure of physics at the smallest scales. Over hundreds of millions of years, gravity amplified these differences. Regions that were slightly denser attracted more matter from surrounding areas, growing denser still. Regions that were slightly less dense gave up their matter to surrounding overdensities, growing emptier over time. This process, running continuously for billions of years under the influence of gravity and the expanding fabric of space-time, is what produced the cosmic web we observe today. The filaments and sheets formed where matter flowed together along sheets of gravitational attraction. The superclusters formed at the intersections where multiple filaments met. And the voids formed in between, where matter was pulled away in every direction, leaving behind volumes of space that grew emptier as the universe aged. When astronomers began cataloging these structures in earnest, starting with surveys like the Center for Astrophysics Redshift Survey in the 1980s, they found voids everywhere they looked. One of the earliest and most striking discoveries was the Boötes Void, identified in 1981 by astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Scheckman. This structure, located in the direction of the constellation Boötes, stretches approximately 300 million light-years across. 300 million light-years is a scale that is genuinely difficult to grasp. Our entire Milky Way galaxy is about 100,000 light-years in diameter. The distance from us to our nearest large galactic neighbor, the Andromeda Galaxy, is about 2.5 million light-years. The Boötes Void could swallow tens of thousands of Milky Way galaxies placed end to end, and the distance across it is more than 100 times the distance from us to Andromeda. At its discovery, the Boötes Void was so large that some astronomers had difficulty believing it was a real structure. The standard cosmological models of the time had trouble explaining how such an enormous empty region could form in a universe that was only 13.8 billion years old. Over time, as more data accumulated and cosmological models improved, astronomers came to understand that the Boötes Void, while extraordinary, is consistent with how the universe evolves, but it remains one of the largest known voids in the observable universe. Inside the Boötes Void, there are some galaxies, but remarkably few. Where a region of that size, in an average part of the universe, might contain 2,000 or more galaxies, the Boötes Void contains roughly 60 that have been identified. These isolated galaxies exist in conditions radically different from galaxies like our own, and studying them tells us things about galaxy evolution that we could not learn any other way. Today, astronomers have cataloged more than 8,000 voids and supervoids across the observable universe. The techniques used to identify and study them have grown increasingly sophisticated. Redshift surveys map the three-dimensional distribution of galaxies, allowing astronomers to identify the walls and filaments of the cosmic web and the empty spaces between them. Statistical methods are used to characterize the sizes, shapes, and properties of voids. And increasingly, voids are being used as precision cosmological tools, yielding measurements of fundamental parameters that describe the universe as a whole. The size distribution of voids follows patterns that are sensitive to cosmological parameters. The rate at which voids grow depends on the expansion history of the universe. The shapes of voids are influenced by the surrounding matter distribution and by the effects of dark energy. All of these properties make voids a kind of cosmic laboratory, one that is spread across billions of light years and has been evolving for billions of years. Let's look more carefully at why voids have the structure they do and why galaxies behave so strangely near their boundaries. In most of the universe, gravity works in the way we intuitively expect it to. Mass attracts mass. Larger concentrations of matter pull surrounding matter toward them. Galaxies fall into clusters. Clusters grow. This is the process that built the cosmic web. But voids present a kind of gravitational inversion. Inside a void, the mass density is extremely low, far below the cosmic average. The galaxies that might have been there have been pulled out over billions of years by the gravitational pull of the dense walls and filaments surrounding the void. As matter evacuates the interior, the remaining matter inside the void is pulled outward in all directions, toward the surrounding dense regions. This creates an environment where gravity effectively acts as a repulsive force with respect to the void interior. Anything inside the void is being pulled toward the walls. Anything outside the void is also being pulled away from the void, toward the dense regions. The result is that the void grows emptier over time, and objects at its edges are accelerated outward away from the void center. This is sometimes described as a void having negative gravity from the perspective of an observer inside it, though that is a simplification. What is actually happening is that the gravitational pull of the surrounding matter is stronger than the gravitational pull of the matter inside the void. So the net effect is a force pointing away from the void center for objects near its edges. For a galaxy trying to enter a void from the outside, this creates a significant barrier. The surrounding dense regions are pulling the galaxy toward them, and the void interior offers almost nothing to pull the galaxy inward. In practice, galaxies do not wander into voids accidentally. They either form there in the rare cases where small density fluctuations within the void seed small amounts of star formation, or they are stranded there by the evacuation of surrounding matter that gradually leaves them isolated. The galaxies that are found inside voids are among the most scientifically interesting objects in the universe, precisely because of their extreme isolation. These void galaxies, as they are called, evolve in a completely different environment from galaxies like the Milky Way. They have no large neighbors to interact with. They are not experiencing tidal forces from nearby massive structures. They are not accreting material from dense filaments. They are, in a very real sense, developing on their own. Studies of void galaxies have found that they tend to be smaller than average galaxies of the same age. They tend to have lower metallicity, meaning their stars contain fewer heavy elements because they have had fewer generations of stars to process primordial hydrogen and helium into heavier atoms. They tend to have a higher fraction of gas relative to stars because the slower pace of star formation has left more of their raw material unconsumed. And they tend to be bluer in color because their ongoing, if slow, star formation produces hot young stars that emit more blue and ultraviolet light. In some respects, void galaxies resemble the galaxies that populated the early universe before the intense interactions of the cosmic web accelerated star formation and processed gas into stars in the densely populated regions. Studying void galaxies may give astronomers a window into early galaxy evolution that is not available elsewhere. Void galaxies also serve as tests of fundamental physics. In standard cosmological models, galaxy evolution depends on the dark matter halo in which the galaxy sits, on the mass of gas available, on interactions with neighbors, and on feedback from star formation and black holes. In voids, many of these factors are minimized or absent. Void galaxies that do not behave as models predict are valuable indicators that something is missing from our understanding. There is one more aspect of voids that makes them uniquely important in modern cosmology, and it involves dark energy. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. Discovered in 1998 through observations of distant supernovae, the accelerating expansion was one of the most surprising findings in the history of physics. In a universe full of matter, gravity should be slowing the expansion down. Instead, something is pushing it faster. That something, which accounts for approximately 68% of the total energy content of the universe, is called dark energy, though that name reflects our ignorance of what it actually is rather than any deep understanding. The simplest and currently most popular explanation for dark energy is the cosmological constant, a term that Einstein originally introduced and then famously discarded, which represents a constant energy density associated with empty space itself. If this explanation is correct, then dark energy exerts a uniform pressure that drives the accelerating expansion everywhere in the universe. But detecting and measuring dark energy is extraordinarily difficult. In regions of the universe where matter is dense, gravity dominates, and the effects of dark energy are masked. Clusters of galaxies are held together by gravity, despite the expansion. Filaments are dense enough that the internal gravitational forces overwhelm the tendency to expand. In these regions, dark energy is present but essentially invisible in its effects. Voids are different. Inside a void, matter density is so low that gravity is minimal. Dark energy, which acts uniformly throughout space, is the dominant force. The expansion of space inside a void is faster than in the average universe because there is less gravity fighting against it. Voids grow not just because matter is pulled out of them by surrounding structures, but because the space inside them is expanding faster than the surrounding regions. This makes voids uniquely powerful laboratories for studying dark energy. The size distribution of voids, their shapes, and the velocities of galaxies at their boundaries are all sensitive to the properties of dark energy in ways that are complementary to other measurement techniques. Using voids as cosmological probes is an active and growing area of research that promises to help pin down the nature of dark energy more precisely than current measurements allow. One particularly clever technique uses a property called the Alcock-Pazinski effect. In principle, voids in the universe should be statistically round on average because there is no preferred direction in the universe. If voids appear elongated or flattened when measured, it indicates that the assumed relationship between redshift and distance is wrong, which in turn gives information about the expansion history of the universe and the properties of dark energy. By measuring the shapes of thousands of voids in redshift surveys, astronomers can constrain cosmological parameters with high precision. Another technique uses voids as a kind of negative lens for gravitational lensing. Massive objects bend light, and galaxy clusters and filaments can be detected by their effect on the images of background galaxies. Voids, having below average mass, bend light in the opposite direction, creating a slight demagnification of background sources. This effect, called void lensing or anti-lensing, is detectable statistically using large surveys and provides independent information about the mass distribution in and around voids. The cosmic microwave background, the afterglow of the Big Bang that permeates the entire universe, is also affected by voids through an effect called the integrated Sachs-Wolf effect. As photons from the cosmic microwave background travel through the universe, they are affected by the gravitational potentials they encounter. When they pass through a region of higher than average density, they gain energy falling in and lose energy climbing out. In a static universe, these effects cancel exactly. But in a universe with dark energy, the potential wells evolve over time, and photons passing through voids gain a slight net amount of energy compared to photons that do not pass through voids. This produces a small correlation between the positions of voids and slightly elevated temperature patches in the cosmic microwave background, and detecting this correlation is another way to probe the properties of dark energy. The Planck satellite, which mapped the cosmic microwave background with extraordinary precision from 2009 to 2013, provided data used in searches for the integrated Sachs-Wolf effect from voids. Results have been consistent with the cosmological constant model of dark energy, though the signal is subtle and the constraints are still relatively weak compared to other methods. Future missions and surveys will improve these measurements significantly. Among the largest and most scientifically significant voids are what are called supervoids. These are voids that exceed several hundred million light-years in diameter, making them among the largest coherent structures in the universe. While individual voids are impressive, supervoids are the dominant features of the very large-scale structure. The Boötes Void, at roughly 300 million light-years, was long considered extraordinarily large, but subsequent surveys have revealed other supervoids of comparable or greater size. One particularly studied supervoid is the cold spot supervoid, located in the direction of the constellation Eridanus and associated with a famously anomalous cool region in the cosmic microwave background called the CMB cold spot. The CMB cold spot was identified in data from the WMAP satellite in the early 2000s. It is a region of the microwave sky that is significantly colder than its surroundings, larger than would be expected from standard cosmological models, and has been a source of debate and investigation ever since. One proposed explanation is that the cold spot is the result of a supervoid along the line of sight, which would cool photons from the cosmic microwave background through the integrated Sachs-Wolf effect. In 2015, a team of astronomers using data from the Pan-STARRS survey identified a supervoid in the direction of the cold spot, located about 3 billion light-years from Earth and spanning roughly 1,800,000,000 light-years across. This would make it one of the largest structures ever identified in the universe. The team found that the supervoid could account for part, though probably not all, of the cold spot anomaly. Whether the full cold spot can be explained by this supervoid, or whether some additional physics is required, remains an open question. 1,800,000,000 light-years. It bears repeating what this means. The entire local group of galaxies, which contains the Milky Way, Andromeda, and more than 50 other galaxies, spans about 10 million light-years. The supervoid associated with the CMB cold spot is 180 times larger than our entire local neighborhood. The number of galaxies it should contain, based on the average density of the universe, is enormous. The number it actually contains is a tiny fraction of that. This brings up a fundamental feature of how voids work that is easy to overlook. Voids are not regions of truly zero density. They contain some matter. They contain some galaxies. They contain dark matter in the form of faint, sparse filaments that even penetrate the void interior. But their density is far below the cosmic average, typically 10 to 30% of the mean density of the universe, with the most extreme voids approaching perhaps 5%. This below-average density is what makes them voids in the formal sense. Cosmologists typically define a void as a region where the density is below some threshold relative to the cosmic mean, and use sophisticated algorithms applied to galaxy survey data to identify and characterize void boundaries, centers, and properties. Different algorithms produce somewhat different catalogs of voids, and a significant amount of work in the field goes into understanding the systematic differences between these approaches and what they imply for derived quantities. The void catalog produced from the Sloan Digital Sky Survey, one of the most comprehensive galaxy surveys ever conducted, contains thousands of voids identified in the distribution of hundreds of millions of observed galaxies. These catalogs have been used to study void statistics, void evolution, and the cosmological implications of the void population. Upcoming surveys, including the Dark Energy Spectroscopic Instrument Survey, the Euclid mission, and the Rubin Observatory Legacy Survey of Space and Time, will map tens or hundreds of millions more galaxies, producing void catalogs of unprecedented size and precision. The picture of void evolution over cosmic time is one of steady growth. In the early universe, voids were small, numerous, and not yet distinct from their surroundings. As gravity worked over billions of years, the overdense regions grew denser, and the underdense regions grew emptier. Small voids grew larger. Adjacent voids merged when the walls between them became too thin to resist the inward pull of surrounding structures. Large voids merged into supervoids. This hierarchical process of void merging mirrors, in some ways, the hierarchical process of structure formation in the matter-dominated regions, where small halos merge into larger halos, and eventually into galaxy clusters. The merging of voids is a particularly interesting phenomenon to study. When two voids grow large enough that their boundaries overlap, the sheet of galaxies forming the shared wall begins to be pulled in both directions simultaneously. Over time, the wall thins out and eventually breaks, allowing the two void interiors to merge into a single larger void. The galaxies from the former wall are pulled toward the outer boundaries, adding to the rims and filaments that surround the merged supervoid. This process is ongoing. The cosmic web is not a static structure, but a dynamic one, evolving continuously as gravity operates across billions of light-years over billions of years. We observe the cosmic web at a snapshot in time, and that snapshot shows voids of many different sizes and ages, from young, small voids just beginning to evacuate their interiors to ancient supervoids that have been growing since the early universe. The ultimate fate of voids, and of the cosmic web as a whole, is determined by dark energy. If dark energy continues to act as a cosmological constant, driving accelerating expansion indefinitely, then the large-scale structure of the universe will eventually be torn apart. Galaxies that are not gravitationally bound to each other will be separated by expanding space that grows faster and faster. The filaments and sheets of the cosmic web will be stretched and thinned. The walls around voids will erode as galaxies are pulled apart from each other. In the very distant future, perhaps 1 trillion years or more from now, the observable universe will look radically different from today. Most galaxies will have moved beyond each other's observable horizon, The cosmic web will have dissolved. What remains, at least locally, will be isolated gravitationally bound structures, individual galaxies or small groups of galaxies, separated by expanding voids that have merged into a single vast emptiness. The universe will be dominated by void. This is not a dramatic or sudden event. It is a gradual process, playing out across timescales that dwarf the current age of the universe. But it is the direction the universe appears to be heading, driven by the dominant force of dark energy. In this far future, there is a curious implication for the question of habitability. Stars will continue to form for a very long time, but the rate of star formation has been declining since it peaked roughly 10 billion years ago, approximately 3 billion years after the Big Bang. Today, the universe forms stars at only a few % of its peak rate. As time goes on, star formation will continue to decline as galaxies exhaust their gas supplies. In the crowded regions of the cosmic web, where galaxies frequently interact and merge, star formation is already suppressed in many large elliptical galaxies whose gas was long ago consumed or heated. In smaller, more isolated galaxies, particularly void galaxies, star formation continues at a slow and steady pace because their gas has not been consumed by intense bursts of activity. In the very long run, it is precisely the isolated void galaxies that may be the last places where new stars are forming. A small, gas-rich dwarf galaxy sitting in the depths of a supervoid, unperturbed by any neighbor, converting its gas to stars at a gentle and efficient pace, could be forming stars long after the galaxies of the cosmic web have exhausted their fuel. The last star in the universe may well be born not in a rich cluster or a large spiral galaxy, but in a lonely dwarf galaxy sitting in the middle of nowhere. The practical implications of this for any hypothetical technological civilization are worth considering, not because we know that such civilizations exist, but because asking the question reveals something about the long-term structure of the universe. A civilization concerned about the long-term persistence of conditions favorable to complex chemistry, liquid water, and energy gradients would, in principle, prefer a location with slow and steady star formation, rather than intense and rapidly depleting activity. Void galaxies offer precisely this: a slower, quieter, longer, lasting stellar environment. The difficulty, of course, is reaching such a place. A void galaxy might be hundreds of millions of light-years away from the nearest large galaxy. Traveling such a distance is beyond anything remotely conceivable with current or near-future technology, and may remain so indefinitely given the fundamental limit imposed by the speed of light. But from a purely astrophysical standpoint, void galaxies have a kind of longevity that more active galaxies lack. This is one of the many ways in which voids force us to think about the universe on timescales and distance scales that are deeply unfamiliar. The universe is not just the Milky Way and its neighbors. It is not just the few billion light-years accessible to current telescope technology. It extends, as far as we know, far beyond what we can observe, and it will continue to exist and evolve for trillions and trillions of years after the current era of stars and galaxies has passed. Voids remind us of this. They are not absences in a universe defined by presence. They are structural features of a universe in which emptiness is the rule and matter is the exception. By volume, voids dominate. The filaments, sheets, and clusters of the cosmic web are remarkable precisely because they are rare concentrations of matter in a universe that trends toward dispersion and emptiness. Let's return to some of the current research frontiers in void science, because there are a number of open questions that are actively being investigated. One of the most important is the precise measurement of what cosmologists call the growth rate of structure. The rate at which matter clusters under gravity depends on the properties of dark matter, dark energy, and gravity itself. Different theoretical models predict slightly different growth rates, and measuring the actual growth rate provides a test of these models. Voids, because they represent the absence of structure, are actually sensitive probes of the growth rate in a complementary way to the measurement of clustering in dense regions. By measuring how the shapes and sizes of voids evolve over cosmic time, and by measuring the velocities of galaxies at void boundaries, cosmologists can infer the growth rate of structure. Current measurements from void surveys are broadly consistent with standard cosmological models, but they are not yet precise enough to definitively rule out alternatives. The next generation of surveys will significantly improve these measurements. Another open question involves the internal structure of voids. While voids are defined by their low density relative to the cosmic mean, they are not perfectly uniform inside. There are subtle density variations within void interiors, residual filaments of dark matter, and small-scale structures associated with the rare void galaxies. Understanding this internal structure more precisely, both through observations and through simulations, is an active area of research. Numerical simulations of the universe, which follow the evolution of dark matter, gas, and galaxies from initial conditions in the early universe to the present day, have become extraordinarily sophisticated. Modern simulations run on the world's largest supercomputers can follow the evolution of hundreds of billions of simulated particles across volumes of space comparable to what we observe. These simulations reproduce the cosmic web, including voids, filaments, sheets, and clusters, with impressive fidelity. They predict the statistical properties of voids that are then compared to observations. One consistent finding from simulations is that voids have a characteristic profile. Moving from the outer wall of a void toward its center, the density drops steeply at first, and then more gradually, reaching a minimum somewhere inside the void, but not necessarily at the geometric center. This profile, and the way it varies with void size and environment, contains information about the growth history of the void and the cosmological context in which it formed. Simulations have also been used to study what happens to dark matter inside voids. Even though voids are defined primarily by their galaxy distribution, dark matter, which makes up roughly 27% of the total energy content of the universe and about 85% of all matter, also occupies void interiors in reduced quantities. The dark matter inside voids is organized into faint filaments and sheets, much less prominent than those outside voids but present nonetheless. These faint internal structures can in principle affect the dynamics of void galaxies and the evolution of the void itself. One fascinating aspect of voids that has received increasing attention is their topology. In the cosmic web, voids are not isolated spheres. They are connected to each other through the sheets and filaments that form their boundaries. In a topological sense, the cosmic web is a single connected structure, and voids are the holes in that structure. Studying the topology of the cosmic web, including how many voids there are, how they are connected, and how these properties change over cosmic time, is a way of characterizing the overall architecture of the universe's large-scale structure. Mathematical tools borrowed from topology, particularly persistent homology, are increasingly being applied to cosmic web data. These tools can identify features like loops and voids in three-dimensional point distributions without requiring the definition of arbitrary density thresholds. Applied to galaxy survey data, they reveal the topological complexity of the cosmic web in ways that complement traditional void-finding algorithms. The connection between voids and the properties of galaxies that live near them, rather than inside them, is another active research area. Galaxies near void boundaries, in the walls and filaments that define the edges of voids, experience different tidal forces and accretion histories than galaxies deep inside filaments or clusters. There is growing evidence that the proximity of a void affects the star formation rates, morphologies, and gas contents of nearby galaxies in measurable ways. This environmental effect of voids adds to the more familiar environmental effects of clusters and filaments. The relationship between voids and the formation of galaxy clusters is also worth noting. Voids and clusters are complementary structures in the cosmic web. Where voids are underdense, clusters are overdense. Where voids are growing emptier, clusters are growing denser. The most massive clusters, called richest clusters or Abel clusters, after the astronomer George Abel, who cataloged them in the 1950s and 60s, tend to form at the intersections of the most prominent filaments, which are themselves typically the boundaries between multiple large voids. This means that the sizes and properties of voids are statistically correlated with the sizes and properties of nearby clusters. Large voids tend to be surrounded by more prominent filaments and more massive clusters. Studying these correlations gives insight into how the overall architecture of the cosmic web developed from the initial density fluctuations of the early universe. The initial density fluctuations themselves have a specific statistical character inherited from the physics of the very early universe, including a period of rapid exponential expansion called inflation that took place in the first fraction of the first second after the Big Bang. Inflation smoothed out large-scale irregularities and imprinted a nearly scale-invariant spectrum of fluctuations. The specific character of this spectrum, including small deviations from perfect scale invariance, called the spectral tilt, has measurable consequences for the statistical properties of the cosmic web and the void distribution. By comparing the measured void distribution to theoretical predictions based on different inflationary models, cosmologists can, in principle, test theories of the very early universe through their imprints on the very large-scale structure of the cosmos. This is one more way in which voids, those vast empty bubbles, connect to the deepest questions in physics. On a more observational note, the challenge of detecting void galaxies and studying them in detail is significant. Because void galaxies are isolated and often intrinsically faint, They require sensitive telescopes and careful observational strategies. Surveys that are optimized for detecting the bright galaxies in clusters and filaments may miss the faint and isolated galaxies in void interiors. Dedicated efforts to identify and study void galaxies have revealed their unusual properties, but have also highlighted how incomplete our census of them remains. Future surveys with greater sensitivity and sky coverage will discover many more void galaxies and allow systematic studies of their properties across a range of void environments. The Square Kilometre Array, a next-generation radio telescope being built in South Africa and Australia, will detect the radio emission from neutral hydrogen gas in galaxies out to large distances, providing a three-dimensional map of the gas content of galaxies across the universe. Since void galaxies tend to be gas-rich, this survey will be particularly valuable for studying the population of galaxies inside voids and understanding how their gas content relates to their isolation. Optical and infrared surveys from facilities like the Vera Rubin Observatory in Chile and the Nancy Grace Roman Space Telescope will provide complementary data on the stellar populations and star formation histories of void galaxies. Combining data from multiple wavelengths will give a comprehensive picture of how galaxy evolution differs inside voids compared to denser environments. There is also important work being done on the smallest scales within voids. What is the minimum halo mass, the minimum concentration of dark matter that can support the formation of a galaxy inside a void? Theoretical predictions and observations suggest that the minimum threshold for galaxy formation may be higher inside voids than outside them, because the reduced density means fewer mergers to build up halo mass and less accretion of gas from surrounding filaments. If this is correct, voids should contain very few extremely faint dwarf galaxies relative to denser regions, and future surveys should be able to test this prediction. The question of whether any objects other than void galaxies inhabit the interiors of voids is also of interest. Black holes can exist wherever there is collapsed matter. Neutron stars, white dwarfs, and other stellar remnants would persist in the stars of void galaxies long after those stars have died. But in the absence of galaxies, there are no stars, and in the absence of stars, there are none of these objects. The deep interiors of the largest voids, far from any void galaxy, are as close to absolute emptiness as the universe provides. Even there, though, the universe is not completely empty. The cosmic microwave background radiation fills the entire universe uniformly, including the inside of voids. Dark matter, while sparse, is present, and a very small number of stray atoms and ions drift through void interiors, part of the diffuse intergalactic medium that, while almost undetectably thin in dense regions, is even thinner inside voids. In quantitative terms, the intergalactic medium inside a typical cosmic void contains roughly 1 to 10 atoms per cubic meter. For reference, the air in the room where you are reading this contains approximately 25,000 billion atoms per cubic meter. The interior of a cosmic void is a far better vacuum than anything achievable with current technology in a laboratory on Earth. Yet, even this near-perfect vacuum has consequences. The diffuse gas inside voids, while almost impossibly thin, can be detected through its effect on light from distant quasars. As the light from a bright quasar travels across the universe, it passes through both dense filaments and through void interiors. The filaments absorb certain wavelengths of light, producing absorption lines in the quasar spectrum. The void interiors produce almost no absorption, providing a way to measure the density of the intergalactic medium inside voids and compare it to the density in filaments. This technique, called absorption spectroscopy, has been used extensively with data from the Hubble Space Telescope and large ground-based telescopes to map the intergalactic medium across a wide range of cosmic environments. The results confirm that void interiors have densities consistent with theoretical predictions and provide constraints on the temperature and ionization state of the intergalactic gas in these extreme environments. The temperature of the intergalactic gas inside voids is another interesting quantity. In dense regions, the gas is heated by the ultraviolet radiation from galaxies and quasars, by shocks from infalling matter, and by feedback from active galactic nuclei. Inside voids, these heating sources are largely absent. The gas can cool more effectively, though it is also less dense and therefore cools less efficiently by radiation. The net result is an intergalactic gas in void interiors that tends to be cooler and less ionized than in dense regions, though still warm by everyday standards at tens of thousands of degrees Celsius. Understanding the temperature and ionization structure of the intergalactic medium inside and outside voids is important for understanding the overall thermal history of the universe. After the Big Bang, the universe was a hot plasma. As it expanded and cooled, Protons and electrons combine to form neutral hydrogen atoms at an event called recombination, roughly 380,000 years after the Big Bang. For the next few 100 million years, the universe was in what is called the cosmic dark ages, before the first stars and galaxies formed and began radiating ultraviolet light that reionized the hydrogen. The epoch of reionization, during which the neutral intergalactic hydrogen was transformed back into ionized plasma by ultraviolet radiation from early galaxies and quasars, is one of the major transitions in cosmic history and a major focus of current observational effort. Voids may have been among the last regions to be reionized, because they were far from the early galaxies producing the ionizing radiation. Understanding the spatial distribution of reionization and how it progressed through the cosmic web, including through voids, is an active research topic. Observations of the 21-centimeter emission and absorption from neutral hydrogen, at wavelengths sensitive to the state of hydrogen in the early universe, may eventually provide direct images of the distribution of neutral hydrogen during and after reionization. Facilities like the Hydrogen Epoch of Reionization Array and future instruments including the Square Kilometer Array LOW are designed to make these observations. The results will tell us how the void regions of the universe participated in the reionization process and how that process shaped the subsequent evolution of the cosmic web. There are many things that scientists do not yet know about voids, and these open questions define the frontier of the field. The precise nature of dark energy remains unknown. Whether it is a cosmological constant, a dynamic field, or something else entirely affects the predicted evolution of voids in ways that future observations will constrain, but that current data cannot definitively resolve. The relationship between the void population and the initial conditions of the universe, and specifically whether voids can tell us more about inflation than other cosmological probes, is being actively investigated. Statistical tests of the void distribution may be able to detect primordial non-Gaussianity, small deviations from perfectly Gaussian random fluctuations in the initial density field that would be evidence of specific inflationary models. The detailed properties of void galaxies, their internal structure, their star formation histories across cosmic time, and their relationship to the dark matter halos they inhabit are not yet well understood. Systematic surveys of these objects are just beginning. The connection between void properties and the formation of life, while highly speculative, raises interesting questions. Void galaxies may be long-lived environments, but they are also lower metallicity environments with fewer heavy elements available for rocky planet formation. The trade-offs between longevity and chemical richness are not straightforward to evaluate, and perhaps most fundamentally, the question of whether our cosmological model is correct remains open. Dark energy and dark matter, which together constitute approximately 95% of the universe's total energy content, are both known only through their gravitational effects. Neither has been detected directly in any laboratory experiment. Voids, as the most extreme environments for dark energy's effects, are one of the places where alternative models might reveal their differences from the standard picture. The universe is mostly nothing, that nothing is dynamic, growing, shaping everything around it, and serving as a laboratory for the most fundamental physics we know. The study of cosmic voids has moved from a curiosity to a central tool of modern cosmology, and the next decade of observations promises to transform our understanding of these vast empty spaces and what they tell us about the nature of reality. The voids are not the absence of the universe. They are a fundamental part of it. They are where the expansion of space is most clearly visible, where dark energy exerts its power most openly, where the fate of the cosmos is written most plainly. And they are everywhere, surrounding us on all sides, stretching for hundreds of millions of light years in every direction beyond the comfortable density of our local cosmic neighborhood. We live in a bubble of matter, surrounded by seas of emptiness. Understanding those seas is one of the great scientific projects of our time. To appreciate just how far our understanding of voids has come, it helps to trace the history of how we came to map the universe's large-scale structure at all. For most of human history, astronomers had no way to know how far away a star or galaxy was. They could measure angles on the sky, track brightness, and observe colors, but translating those measurements into actual distances required a sequence of clever methods that took centuries to develop. The first rungs of what astronomers call the cosmic distance ladder were established using parallax, the slight shift in apparent position of nearby stars as the Earth orbits the Sunday. This works for stars within a few thousand light years of Earth. For more distant objects, astronomers rely on standard candles, objects whose intrinsic brightness is known, so that the apparent brightness tells you the distance. Cepheid variable stars, which pulsate with a period that is directly related to their true luminosity, were the key to measuring distances to nearby galaxies in the early 20th century. The astronomer Henrietta Swan-Leavitt discovered this period luminosity relationship in 1912 by studying Cepheids in the Small Magellanic Cloud. Using Cepheids, Edwin Hubble measured the distance to the Andromeda Galaxy in 1923 and showed definitively that it lay far outside the Milky Way. This established that the Milky Way is one galaxy among many, and the scale of the universe expanded overnight from hundreds of thousands of light years to millions and eventually billions. Hubble also discovered, using redshift measurements from Vesto Slipher and others, that distant galaxies were receding from us with velocities proportional to their distances. This relationship, now called Hubble's law, revealed that the universe is expanding. Working backward in time from an expanding universe leads to the conclusion that everything was once compacted into a hot, dense state, the Big Bang. With the concept of cosmic expansion established, redshift became a tool for measuring distances. The redshift of a galaxy's light, caused by the stretching of light waves as the universe expands, tells you how much the universe has expanded since the light was emitted. Combined with a model of the expansion history, redshift gives distance. This is the basis of all large-scale redshift surveys, which measure the positions and redshifts of thousands or millions of galaxies to construct three-dimensional maps of the universe. The first hint that the universe had large-scale structure came from the discovery of clusters of galaxies in the early 20th century. Harlow Shapley and Adelaide Ames cataloged thousands of galaxies in the 1930s and noted that they were not uniformly distributed. Fritz Zwicky, studying the Coma cluster in the 1930s, found that the galaxies were moving too fast to be held together by the visible mass alone, and postulated the existence of additional invisible mass, what we now call dark matter. The true extent of cosmic structure began to emerge with the CFA redshift survey in the 1970s and 80s, led by Margaret Geller, John Huchra, and colleagues at the Harvard-Smithsonian Center for Astrophysics. The first CFA slice, published in 1986, revealed a strikingly thin sheet of galaxies stretching across the survey volume, which became known as the Great Wall. It was the largest known structure at the time, at roughly 500 million light-years long, and surrounding it, clearly visible in the two-dimensional slice of the survey, were large empty regions, voids. The Great Wall and the surrounding voids made an immediate impression on the scientific community. The structure was so pronounced that it seemed almost too organized to have formed by gravitational collapse alone in the time available since the Big Bang. Some astronomers initially worried that it might challenge the standard cosmological model. In time, better simulations and more data showed that such structures are consistent with standard cosmology, but the discovery marked a turning point in how astronomers thought about the universe. Subsequent surveys pushed to greater distances and larger volumes. The 2-degree field galaxy redshift survey, completed in the early 2000s, mapped over 200,000 galaxies. The Sloan Digital Sky Survey, which began collecting data in 2000 and continues to this day in various forms, has now observed hundreds of millions of objects and mapped the three-dimensional distribution of galaxies across a significant fraction of the observable universe. These surveys have confirmed and extended the picture of the cosmic web. Voids appear at every scale the surveys can probe. The statistical properties of voids have been measured and compared to theoretical predictions. The correlations between void properties and galaxy properties have been quantified. The cosmic web is not a simple structure, but a richly complex one, with voids and filaments and clusters organized in a hierarchy that extends from small scales all the way to the largest scales accessible to observation. The three-dimensional maps produced by redshift surveys are not perfect representations of the true three-dimensional distribution of galaxies. Redshift is not a perfect distance indicator because galaxies also have peculiar velocities. Velocities caused by gravitational interactions with their neighbors that are superimposed on the smooth Hubble flow. A galaxy that is at a given distance from us, but moving toward us, will appear to have a lower redshift than its distance would imply, and vice versa. This distorts the apparent shapes of structures in redshift space, an effect called redshift space distortions. Redshift space distortions are an annoyance in some contexts because they complicate the interpretation of maps, but they are also a signal in their own right because they depend on the rate at which structure is growing. Measuring redshift space distortions carefully gives information about the growth of structure, and therefore about dark energy and gravity. Voids are particularly useful here because the coherent outflow of galaxies from void interiors produces a distinctive pattern of redshift space distortions around voids, sometimes called the void galaxy cross-correlation function. The void galaxy cross-correlation function has been measured in several surveys and used to constrain cosmological parameters. The signal is consistent with standard cosmological models, but the precision is limited by the size of current surveys. Future surveys will measure this signal with much greater precision and potentially reveal deviations from the standard model if any exist. Beyond redshift surveys, voids have been studied using weak gravitational lensing. When light from distant galaxies passes near massive objects, the paths of the photons are bent by gravity, distorting the apparent shapes of the background galaxies. By measuring the statistical alignment of many galaxy shapes, astronomers can map the distribution of mass in the universe, including dark matter that cannot be seen directly. The weak lensing signature around voids, where the below-average mass causes a slight anti-lensing or demagnification effect, has been detected in several surveys. The signal depends on the mass profile of voids, and comparing measured profiles to theoretical predictions provides a test of the cosmological model. Combined with the redshift space distortion signal, weak lensing measurements of voids provide a particularly powerful test because the two signals depend differently on the ratio of the growth rate to the expansion rate, which is diagnostic of different gravity theories. Modifications to general relativity proposed as alternatives to dark energy for explaining the accelerating expansion typically predict different growth rates for a given expansion history. By measuring both the expansion rate, through the distance-redshift relation, and the growth rate, through redshift space distortions and weak lensing, and by comparing the two, cosmologists can test whether general relativity correctly describes gravity on cosmic scales. Voids are valuable probes for both of these measurements. The current consensus is that general relativity passes these tests. The measurements are consistent with a universe where general relativity holds and dark energy takes the form of a cosmological constant. But the precision of current tests leaves room for alternatives. The next generation of surveys will tighten the constraints significantly and will either confirm the standard model more firmly or find evidence of deviations that would point toward new physics. Thinking about the universe on these vast scales naturally raises questions about what it would be like to be an observer deep inside a cosmic void. In the observable universe today, any astronomer pointing their telescope at the sky sees thousands or millions of galaxies, depending on the sensitivity of their instrument. The night sky, if we could see galaxies with our naked eyes, would be filled with faint smudges of light in every direction. But an observer located near the center of the Boötes Void or another large supervoid would see almost none of this. In the nearest few 100 million light-years in every direction, there would be almost no galaxies. The night sky, even with a powerful telescope, would show only the most distant, faint galaxies at the very edge of the void, hundreds of millions of light-years away, plus the occasional isolated void galaxy nearby. Such an observer, lacking the evidence of a rich cosmic web visible in our sky, might take much longer to discover the large-scale structure of the universe. They would see far fewer galaxies to survey, fewer data points to map. The void itself might seem like the whole universe if their telescopes were not quite sensitive enough to see its boundaries. This is a sobering reminder of how much our scientific understanding depends on our particular location in the cosmic web. We happen to live in a relatively dense region, surrounded by the Virgo supercluster and the cosmic web, and this has given us an excellent vantage point for mapping the large-scale structure. The question of our own local situation is worth spending some time on. The Milky Way is not a typical galaxy in a typical location. We are part of the Local Group, a collection of more than 50 galaxies dominated by the Milky Way and Andromeda. The Local Group is itself part of the larger Virgo supercluster, sometimes called the Local Supercluster, which contains more than 1,300 galaxy groups and clusters within a region about 100 million light-years across. In 2014, a team of astronomers led by Brent Tully used a new technique to map the boundaries of our supercluster. Rather than simply counting galaxies, they mapped the peculiar velocity field of galaxies, tracing the flows of matter toward dense attractors. They found that the Milky Way sits within a vast supercluster they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea spans roughly 520 million light-years and contains the mass of approximately 100 million billion suns. The edge of Laniakea is defined not by an absence of galaxies, but by a division in the flow of matter. Within Laniakea, galaxies flow toward a central attractor in the direction of the Shapley supercluster. Beyond Laniakea's boundary, galaxies flow toward different attractors in other superclusters. This dividing line, where the cosmic flow field transitions from inward to outward, traces the edge of our gravitational basin of attraction. And surrounding Laniakea, adjacent to its boundaries, is the local void, one of the structures that defines our immediate cosmic neighborhood. The local void is an empty region, approximately 200 million light-years across that borders the Virgo supercluster. The Milky Way and its neighbors are being pushed away from the local void at hundreds of kilometers per second, a motion that was first identified in the 1980s as an anomalous bulk flow of nearby galaxies. This motion is not caused by something pulling us towards some distant attractor, though that explanation was initially popular in the form of the so-called Great Attractor. It is partly caused by the void pushing us away through the same mechanism we discussed earlier. The below-average mass density of the void means that the net gravitational force on galaxies at its boundary points away from the void center. We are being repelled by nothing, or more precisely, we are feeling the net effect of the mass distribution around us, which includes a large underdense region on one side. Understanding the peculiar velocity field of our local universe, including the influence of the local void and other nearby structures, has implications for measuring the Hubble constant, the rate at which the universe is expanding. Because peculiar velocities are superimposed on the Hubble flow, galaxy redshifts in our immediate cosmic neighborhood are systematically affected by local structure. Correcting for these effects requires knowing the local peculiar velocity field accurately, which in turn requires knowing the density field of the cosmic web in our vicinity. The Hubble constant is currently one of the most contested measurements in cosmology. Different methods of measuring it give results that are in significant tension with each other, a discrepancy called the Hubble tension. Early universe measurements, based on the cosmic microwave background and standard cosmological models, give a value of approximately 67 kilometers per second per megaparsec. Late universe measurements, based on the cosmic distance ladder, including Cepheids and Type Ia supernovae, give values closer to 73 kilometers per second per megaparsec. This discrepancy is statistically significant and has resisted explanation within the standard cosmological model. Whether systematic errors in the measurements, new physics beyond the standard model, or some other factors responsible for the Hubble tension remains unclear. But the local cosmic environment, including the effects of the local void and other nearby structures, is one of the considerations that researchers are examining. If the local measurement of the Hubble constant is systematically biased by our particular location in the cosmic web, this could contribute to the discrepancy. Understanding the local void environment is therefore relevant not just to void science, but to one of the most pressing unsolved problems in cosmology. There is something philosophically interesting about the fact that voids, defined by absence, are connected to so many of the most important and active research questions in cosmology: dark energy, dark matter, the growth of structure, the Hubble tension, the epoch of reionization, the long-term fate of the universe. All of these topics have connections to the study of voids. Absence, it turns out, is not nothing. It is information. The places where matter is not tell us about the processes that moved it away, about the forces that shape the distribution of matter over cosmic time, about the properties of the invisible components of the universe. In science, it is often the anomalies, the gaps, the things that are missing or out of place, that carry the most information. Cosmic voids are the universe's gaps. They are the spaces left over when gravity gathered matter into the filaments and clusters of the cosmic web. They are the inverse image of the structure we can see, encoding information about the forces and fields that shape the universe just as surely as the galaxies and clusters do. And in an ironic way, the very emptiness of voids makes them easier to study in some respects. Because there is so little going on inside them, the physics is simpler. And the effects of dark energy are more cleanly separated from the complicated astrophysics of gas, stars, and feedback that dominate in denser regions. The next decade will see a revolution in our ability to map and study voids. The Dark Energy Spectroscopic Instrument, which began full survey operations in 2021, aims to measure the spectroscopic redshifts of approximately 40 million galaxies and quasars over 5 years. This survey will produce the largest and most detailed three-dimensional map of the universe ever created and will yield a void catalog of unprecedented completeness and precision. The Euclid satellite, launched by the European Space Agency in 2023, will conduct a photometric and spectroscopic survey of billions of galaxies across more than 1/3 of the sky, reaching out to redshifts of 2 and beyond. This survey will trace the evolution of the cosmic web, including its void population, from the present day back to when the universe was roughly 3 billion years old, covering most of the period during which dark energy has dominated the expansion. The Vera Rubin Observatory's Legacy Survey of Space and Time will photograph the southern sky repeatedly over 10 years with unprecedented depth and area, producing a photometric survey of billions of galaxies. While primarily a photometric survey without spectroscopic redshifts for most sources, it will enable statistical studies of voids through techniques like photometric redshifts and weak lensing that do not require spectroscopy for every source. The Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will conduct a wide-field survey of galaxies, including spectroscopic observations of millions of targets. Its combination of wide-field, infrared coverage, and high sensitivity will complement other surveys and extend void studies to higher redshifts. Together, these facilities represent an investment of billions of dollars and the effort of thousands of scientists in mapping the universe's large-scale structure with precision sufficient to test cosmological models at the percent level. Voids will be among the most valuable features of the universe revealed by these surveys, and the constraints they provide on dark energy, dark matter, and the growth of structure will be among the most important results of this era of astronomy. The study of cosmic voids sits at the intersection of observational astronomy, cosmological theory, and fundamental physics. It requires the largest telescopes, the most sophisticated simulations, and the most careful statistical analysis. It connects the properties of individual galaxies, which form and evolve in ways sensitive to their local environment, to the properties of the universe as a whole, encoded in the statistics of the void population. We began by noting that the vast majority of the universe, by volume, is empty. That emptiness is not a backdrop to the story of the cosmos, it is a protagonist. The voids grew from the same initial fluctuations that produced the galaxies and clusters we find beautiful and fascinating. They evolved under the same laws of physics. They contain within their structure information about the same fundamental parameters that govern everything else. And their future is the same as the future of everything, increasingly dominated by dark energy, increasingly empty, increasingly isolated. The universe is mostly void. Understanding the void is understanding the universe. What remains to be discovered is enormous. We do not know what dark energy is. We do not know whether the Hubble tension points to new physics or to systematic errors in current measurements. We do not know the full census of void galaxies and their properties. We do not know precisely how the void environment affects the formation and evolution of the rare galaxies that inhabit it. We do not know the detailed statistics of voids at the highest redshifts, where the cosmic web was just forming. Each of these questions will be addressed by current and future observations. The answers will not only tell us more about voids, they will tell us more about the nature of the universe itself, about the forces that shaped it, and about its ultimate destiny. For now, voids remain the vast, quiet, nearly empty spaces that surround every structure we know. They grow slowly, merge gradually, and will eventually dominate everything. They are the future written in the present, the emptiness into which the cosmos is headed, one expanding bubble at a time. To understand cosmic voids more completely, it is worth zooming in on the physical processes that govern the evolution of matter on cosmological scales, because these processes are what created voids in the first place, and what continue to shape them today. In the immediate aftermath of the Big Bang, the universe was a hot, dense plasma of fundamental particles. Photons, quarks, electrons, and other particles existed in a state of thermal equilibrium, constantly interacting and exchanging energy. As the universe expanded and cooled, quarks combined into protons and neutrons, and eventually protons and neutrons combined into the lightest atomic nuclei, hydrogen, helium, and small amounts of lithium. This process, called Big Bang nucleosynthesis, occurred in the first few minutes after the Big Bang and set the initial composition of the universe. Roughly 75% hydrogen and 25% helium by mass, with trace amounts of other elements. For the next several 100,000 years, the universe remained a plasma too hot for electrons to combine with nuclei to form neutral atoms. Photons interacted constantly with the free electrons, making the plasma opaque. The universe was bright, but completely invisible, because light could not travel any distance without scattering off an electron. At approximately 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons to form neutral hydrogen atoms. This event, called recombination, was transformative. Suddenly, the photons could travel freely, and the universe became transparent. Those photons have been traveling ever since, cooling and stretching as the universe expanded. and we detect them today as the cosmic microwave background. The tiny temperature fluctuations in the cosmic microwave background correspond directly to the small density fluctuations in the plasma at the time of recombination. The same fluctuations that would eventually grow into the cosmic web we see today. After recombination came the cosmic dark ages. The universe was filled with neutral hydrogen and helium gas. There were no stars, no galaxies, and no sources of light. For hundreds of millions of years, the universe was dark, but gravity was working. The density fluctuations inherited from the primordial plasma began to grow. Regions that were slightly overdense attracted more matter and became denser. Regions that were slightly underdense lost matter and became emptier. This growth proceeded differently in overdense and underdense regions. In overdense regions, gravity caused matter to collapse, forming the first dark matter halos, the gravitational wells into which ordinary matter fell to form the first stars and galaxies. In underdense regions, matter flowed outward toward the overdense surroundings, evacuating the voids. The first stars, called population 3 stars, formed sometime in the first few 100 million years after the Big Bang. They were massive, hot, and short-lived, burning through their fuel in a few million years before exploding as supernovae. These early supernovae produced the first heavy elements beyond hydrogen and helium, beginning the process of chemical enrichment that over billions of years would produce all the elements needed for rocky planets and complex chemistry. The ultraviolet radiation from these first stars also began the process of reionization, ionizing the neutral hydrogen that had dominated the intergalactic medium since recombination. Reionization was not instantaneous. It proceeded bubble by bubble, as regions around individual galaxies or groups of galaxies were ionized, and these bubbles grew and eventually merged to fill the intergalactic medium. The process was largely complete by about 1 billion years after the Big Bang, though some late finishing regions may have remained partially neutral until later. Voids played a specific role in reionization. Because voids were far from the early galaxies producing ionizing radiation, they were among the last regions to be reionized. The neutral hydrogen in void interiors persisted longer than in denser regions, and the properties of the intergalactic medium in voids during and after reionization differed from the properties in denser regions in ways that are in principle detectable. Mapping the reionization history in different environments, including inside and outside voids, is one of the goals of next-generation radio observations. After reionization, the large-scale structure of the universe continued to develop. The cosmic web became more prominent as density contrasts grew, filaments thickened, clusters grew more massive, and voids grew larger and emptier. By several billion years after the Big Bang, the cosmic web had taken on something close to its present appearance, with large supervoids adjacent to prominent superclusters. The growth of structure has been slowing down since dark energy began to dominate the energy content of the universe, which happened approximately 5 billion years ago, when the universe was roughly 8.8 billion years old. Before that, matter dominated the energy budget, and gravity was the primary driver of structure formation. After that, dark energy's repulsive effect began to compete with gravity, slowing the growth of structure. This transition from matter domination to dark energy domination is visible in observations. The growth rate of structure is measured to be slower today than it was several billion years ago, consistent with the influence of dark energy. Voids provide a way to measure this transition directly because the rate at which voids grow and the velocity field around them are sensitive to the competition between gravity and dark energy. The current epoch in cosmic history is sometimes called the dark energy era. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Ordinary matter, the stuff that makes up stars, planets, gas, and everything we can directly observe, makes up only about 5%. This breakdown has profound implications for understanding the universe. Dark matter, while constituting most of the matter in the universe, interacts with ordinary matter and light only through gravity. It does not emit or absorb electromagnetic radiation of any kind. Its existence was inferred from its gravitational effects on the motions of stars in galaxies, the motions of galaxies in clusters, and the bending of light around clusters. Its nature remains unknown. The leading candidates are various types of weakly interacting massive particles, but despite extensive laboratory searches and indirect astrophysical searches, no dark matter particle has been detected directly. Inside voids, dark matter is present in reduced quantities. The dark matter halos that host galaxies are smaller and less massive in void environments because less mass was available to collapse. The faint filaments of dark matter that penetrate void interiors are remnants of the primordial density fluctuations that were not quite zero inside what became voids. Detecting these faint dark matter structures directly is not possible with current technology, but they leave imprints in the distribution of galaxies and in weak lensing measurements. Dark energy is even more mysterious than dark matter. Unlike dark matter, which at least interacts gravitationally in the same way as ordinary matter, dark energy has a negative pressure that drives the accelerating expansion. No known particle or field accounts for this property naturally. The cosmological constant, Einstein's original term representing the energy of empty space, fits the data well, but has a value that is incomprehensibly small compared to theoretical predictions from quantum field theory. This discrepancy, sometimes called the vacuum energy problem or the cosmological constant problem, is one of the deepest unsolved problems in theoretical physics. Alternative explanations for dark energy include dynamical scalar fields, modifications to general relativity, and more exotic possibilities involving extra dimensions or new fundamental interactions. All of these alternatives make predictions for the growth rate of structure and the expansion history of the universe that differ subtly from the cosmological constant model. Voids, as the primary environment where dark energy's effects are most cleanly observable, are key testing grounds for these alternatives. The next generation of surveys will constrain the equation of state of dark energy, a parameter that describes how the energy density of dark energy changes with time with unprecedented precision. If the equation of state differs from -1, which is the value predicted by the cosmological constant, it would indicate that dark energy is dynamic and would rule out the simplest explanation. Current measurements are consistent with -1, but with error bars large enough to allow significant deviations. Future surveys aim to reduce those error bars by a factor of several to 10, potentially resolving whether dark energy is a constant or a dynamic field. This is not purely an academic exercise. The nature of dark energy determines the ultimate fate of the universe. If dark energy is a cosmological constant, the universe will continue expanding forever, with galaxies gradually moving beyond each other's observable horizons, stars eventually exhausting their fuel, and the universe cooling toward a state of maximum entropy. If dark energy is a dynamic field, it might weaken over time, eventually allowing gravity to halt the expansion and cause a big crunch, or it might strengthen over time, eventually tearing apart not just the cosmic web, but individual galaxies, stars, planets, and even atoms in an event called the Big Rip. Voids are the window through which we are most clearly watching dark energy at work. They are the experiment running at the largest scales, on the longest timescales, with the fewest confounding factors. Every measurement of a void, every catalogued void galaxy, every statistical analysis of the void population is a data point in our effort to understand this mysterious dominant component of the universe. The history of science is full of examples where studying something apparently simple or empty turned out to be profoundly informative. The study of the vacuum in quantum mechanics led to the discovery of virtual particles and quantum fluctuations. The study of empty space in general relativity led to the prediction of gravitational waves. The study of cosmic voids is following this tradition, using the emptiness itself as a tool to probe the deepest properties of nature. What began as a surprising observation, that the universe has large empty regions that were not expected, has grown into one of the most fruitful areas of modern cosmology. The tools for studying voids have become increasingly sophisticated. The surveys mapping them have become increasingly comprehensive. The theoretical understanding of their formation and evolution has become increasingly precise. And the questions they are being used to answer about dark energy, dark matter, gravity, and the ultimate fate of the universe are among the most fundamental questions in all of science. The cosmic voids are vast, and they are silent, and they are growing, but they are not empty of meaning. In their enormous quiet spaces, the most important physics of the cosmos is on display. The future of the universe is being written in the expansion of nothing, in the merging of bubbles of emptiness, in the gradual dissolution of the beautiful and intricate structure that gravity has spent billions of years building. Understanding that future requires understanding the voids, and understanding the voids is, in a very real sense, understanding the universe. It is worth examining in more concrete terms what scientists actually do when they study voids. The process begins with data, typically a galaxy survey that maps the positions of hundreds of thousands or millions of galaxies across a significant volume of the universe. These surveys measure redshifts, which give distances, and combine them with angular positions on the sky to produce a three-dimensional catalog of galaxy positions. From this catalog, astronomers use void-finding algorithms to identify regions of below-average galaxy density and classify them as voids. Several different algorithms have been developed, each with different strengths and weaknesses. One common approach, called Zobov, finds density minima in the galaxy distribution and grows zones around them, merging zones until the boundary density rises above a threshold. Another approach, called Void, partitions space using a technique called Voronoi tessellation and then identifies underdense cells, combining adjacent underdense cells into voids. Still, other approaches work directly in redshift space, using the galaxy distribution without correcting for peculiar velocities. Each of these methods produces a void catalog with somewhat different properties. Comparing the results of different methods on the same data reveals how sensitive the void statistics are to the definition of a void and the specific algorithm used. This sensitivity is an important systematic uncertainty in void cosmology that must be carefully controlled to extract reliable cosmological information. Once a void catalog is in hand, the next step is to measure the properties of the voids it contains. The most basic property is the void size, typically parameterized as an effective radius, assuming each void is a sphere. The distribution of void radii, called the void size function, is a statistic that can be compared to theoretical predictions. Larger voids are rarer than smaller voids, and the precise relationship between size and abundance depends on cosmological parameters, particularly the amplitude of the initial density fluctuations and the nature of dark energy. The void profiles, meaning how the galaxy density varies from the center of a void to its boundary, are another important statistic. Theory predicts that void profiles follow a specific shape with a density minimum near the center, a gradual rise to the cosmic mean density somewhere before the boundary, and a slight overdensity called the compensation wall at the void edge. This overdense wall represents the shell of matter that has been evacuated from the void interior and accumulated at the boundary. Measuring void profiles in survey data and comparing them to theoretical predictions tests our understanding of void evolution. The profiles depend on the growth of structure, and therefore on cosmological parameters. They also depend on the relationship between galaxies and dark matter, specifically on how well galaxies trace the underlying dark matter distribution. This relationship, called galaxy bias, is a nuisance parameter that must be modeled or marginalized over when extracting cosmological information from void measurements. The velocity field around voids, meaning how fast galaxies at different distances from the void center are moving, is another powerful statistic. Inside voids, galaxies are moving outward, away from the void center and toward the overdense boundary. At the boundary, galaxies are moving toward the surrounding dense regions. This velocity field is imprinted on the redshifts of galaxies, creating the distinctive pattern of redshift space distortions mentioned earlier. Measuring this velocity field requires observations of many galaxies around many voids, because the signal from any individual void is too noisy. By stacking the redshift space distribution around thousands of voids, averaging out the individual differences, the statistical signal of the coherent outflow from void interiors becomes detectable. The amplitude and shape of this stacked signal depend on the growth rate of structure, which is one of the key quantities cosmologists want to measure. The technical details of these measurements are complex, involving careful treatment of survey selection effects, galaxy completeness, and statistical estimation. But the basic principle is simple. The universe has left specific fingerprints in the distribution and velocities of galaxies around voids, and reading those fingerprints tells us about the physics that produced them. Moving from the technical to the conceptual, it is striking to consider what the existence of cosmic voids implies about the nature of the universe. We live in a universe that started extremely uniform, with density variations of only about 1 part in 100,000, and over 13.8 billion years has developed enormous contrasts between the densest clusters and the emptiest voids. The density contrast between the center of a rich galaxy cluster and the center of a large void spans many orders of magnitude. This is the consequence of gravity acting over cosmic time, a force that is barely detectable between everyday objects. Gravity becomes the dominant force on cosmic scales, shaping the distribution of matter across hundreds of millions of light years. Its patient operation, pulling matter together here and leaving emptiness there, has produced the intricate structure we observe. The cosmic web, with its voids and filaments, is in some ways an analog of other complex structures in nature that arise from simple rules operating over many iterations. The branching pattern of river deltas, the structure of neural networks, and the distribution of cracks in drying mud all show similar hierarchical, scale-free complexity arising from simple physical principles. In each case, the structure encodes information about the process that created it. The cosmic web encodes information about gravity, dark matter, dark energy, and the initial conditions of the universe. Reading that information is the task of observational cosmology. Voids are one of the most legible parts of that encoded record, because their emptiness makes the relevant signals cleaner and easier to interpret. There is also something remarkable about the scale of cosmic voids compared to human experience. The largest voids span hundreds of millions of light years. Light takes hundreds of millions of years to cross them. The entire history of complex life on Earth, from the Cambrian explosion to the present day, covers only about 530 million years. The universe has been large enough to contain these voids for most of its history, and they have been quietly growing for all that time, indifferent to the brief flicker of biological and technological activity on one small planet near the edge of one ordinary galaxy in the wall of one such void. This perspective, simultaneously humbling and exhilarating, is one of the gifts that cosmology offers. The universe is vastly larger, older, and stranger than everyday experience would suggest. Its dominant feature by volume is emptiness. Its most mysterious components, dark matter and dark energy, are invisible and poorly understood. And yet the patterns they have created across billions of light years follow physical laws precise enough to be measured and tested. Science does not make the universe less awe-inspiring. It reveals the actual nature of the awe, which is not mysterious precisely because it is unknown, but profound precisely because it is knowable. The voids are real. They follow real physical laws. Those laws can be understood and tested, and the effort to understand them is one of the most ambitious and ongoing projects in human intellectual history. Research into cosmic voids continues to accelerate. New papers appear constantly as astronomers apply new techniques to new data, as simulators build ever more detailed models of the cosmic web, and as theorists develop new predictions to test. The field has matured from a novelty into a mainstream tool of precision cosmology, and its most important results likely still lie ahead. The surveys of the next decade will provide void catalogs larger by an order of magnitude or more than those available today. The precision of cosmological constraints from voids will improve dramatically. If the Hubble tension has a cosmological explanation, voids may help reveal it. If dark energy deviates from the cosmological constant, voids may be the measurement that detects it. If general relativity breaks down on cosmological scales, voids may be where the deviation first appears with statistical significance. Or the next decade of void science may confirm, with higher precision than ever before, that the standard cosmological model is correct. A universe dominated by dark energy and dark matter, governed by general relativity, expanding from a hot Big Bang, and developing large-scale structure through gravitational amplification of primordial quantum fluctuations. That would also be a profound result, telling us that our simple model describes an extraordinarily complex universe with remarkable accuracy. Either way, the voids will continue to grow, the universe will continue to expand, the cosmic web will continue to evolve, and the vast, quiet, nearly empty spaces that dominate the observable universe will continue to contain, in their structure and their statistics, some of the deepest information we have about the nature of reality. The study of what is not there turns out to tell us a great deal about everything that is. One final dimension of void science deserves attention, and it involves what voids can tell us about the very beginning of the universe and the physics of the earliest moments. The initial density fluctuations that seeded the cosmic web, and from which voids ultimately formed, were laid down during an epoch called inflation. Inflation is a theoretical period of extraordinarily rapid exponential expansion that is believed to have occurred in the first tiny fraction of the first second after the Big Bang, expanding the universe by an enormous factor in an incredibly short time. The exact duration and character of inflation are not yet known. Many different inflationary models have been proposed, differing in their predictions for the statistics of the primordial density fluctuations. The simplest models predict that these fluctuations should have a nearly Gaussian distribution and a nearly scale-invariant power spectrum. Current observations of the cosmic microwave background and large-scale structure are consistent with these predictions, but with finite precision. More precise measurements of the statistical properties of the cosmic web, including the void population, could potentially detect deviations from Gaussianity or perfect scale invariance that would discriminate between different inflationary models. This is an ambitious goal, because the predicted deviations are small and the required measurements are technically challenging. But it represents a remarkable scientific aspiration, using the distribution of the largest structures in the universe to learn about physics at energies and timescales far beyond anything accessible to particle accelerators. The void abundance at very large scales is particularly sensitive to a quantity called primordial non-Gaussianity. If the initial density fluctuations had a non-Gaussian character, the abundance of the largest voids would be affected in a calculable way. Searching for this effect in current and future void catalogs is an active area of theoretical and observational work. A detection would be direct evidence of specific inflationary physics. Non-detection with high precision would constrain the parameter space of inflationary models significantly. This connection between the largest structures in the present-day universe and the physics of the earliest moments is one of the most beautiful aspects of cosmology. The cosmic web is not just a snapshot of where matter ended up. It is a record, encoded in statistical form, of the conditions that existed in the first moments of the universe's existence. Reading that record requires careful observation and sophisticated analysis, but the information is there, written across billions of light years. Voids are an important part of that record. They are not the most obvious features of the cosmic web. Galaxies and clusters are more luminous and more studied. But they are among the most informative, because their large-scale statistics are sensitive to cosmological parameters in ways that complement and extend what can be learned from clustering in dense regions. As this era of precision cosmology unfolds, with surveys mapping billions of galaxies and simulations modeling the evolution of hundreds of billions of dark matter particles, the science of voids will continue to grow in importance and in insight. The questions being asked are fundamental, the tools being developed are powerful, and the universe itself, patient and enormous, contains all the answers in its structure, waiting to be read. The vast majority of the cosmos is voids. That is where the story of the universe's past, present, and future is most clearly written. In closing, consider a single fact that encapsulates the strangeness of the universe we inhabit. If you were to take the entire observable universe, everything within approximately 46 billion light-years of Earth, and ask what fraction of that volume contains anything at all by the standard of average cosmic density, the answer would be a small minority. The dominant state of the universe is void. The cosmic web, with all its filaments and clusters, and the hundreds of billions of galaxies it contains, occupies a fraction of the total volume. The rest is the quiet, expanding, dark energy-filled emptiness of cosmic voids. We are the exception, not the rule. The matter, the stars, the planets, the chemistry, and the biology that fill our experience are concentrated into a vanishingly small portion of what exists. The universe's default state, the condition that describes most of its volume throughout most of its history and increasingly into its future, is emptiness. That emptiness is not passive, not static, and not irrelevant. It is the context in which everything we know exists, the dominant feature of the reality we inhabit, and one of the most powerful tools we have for understanding the cosmos. The voids grow, the universe expands into them and through them, and in their measured, patient emptiness, they carry the information we need to understand where the universe came from and where it is going.